Good afternoon, everybody. Today, we will explore electromagnetic waves. Let's back up a little bit where we were when we left this subject last. We started with Maxwell equation number 2, Faraday's law, which originally started as the circuital law. And we combined that with Maxwell 4, Ampere Maxwell's equation. And we used the sourceless versions of that. What we mean by sourceless is that we said that there's no charges and there are no currents. So rho and J are 0. Now, that does not mean that there's not really a source, because a time-varying electric field can be a source for a magnetic field, and a time-varying magnetic field can be a source for an electric field. So doesn't mean that we have no generation of electromagnetic fields, but it just means that there's no currents and no charge densities. That's what we mean by sourceless. So we use those, and then we use Maxwell 4, which uses that new displacement current, which says that there's a time-varying electric field, that if you take the flux going through an Amperian surface, that there is a magnetic field generated that is then related to the line integral of that B field over the contour of that Amperian surface. So that's the path that takes you from the electric field with a time variation to a magnetic field. And then the Maxwell 2 does the reverse. So we have a time varying magnetic flux going through an Amperian surface. And that time varying flux is then related to the electromagnetic field, electromagnetic force, or just the E field, that is then related to the E field integrated over the line that is on the edge of that Amperian surface. So those two things together were giving us this two equations that said, okay, you can go from B to E and then from E to B again. And then we combined those two in a very specific case where we said, if we assume that there's an electric field that's pointing in the X direction, and there's a magnetic field that's pointing in the Y direction, what do those two equations look like? And we made several simplifications, and we arrived at this wave equation that was either described exclusively for an electric field or for a magnetic field. So it was a second order differential equation that had second order of derivative of Z and a second order derivative of T. And the equation for B and the equation for E looked identical. And we solved the one for E, but that does mean that the solution for B looks exactly the same. And I made the point that if you have the solution for E, then you've already locked in what the B field looks like. And the same way for B, if you have the solution for B, then you already know what the E field looks like. So even though there are two wave equations, they're not completely independent. And we found that the solutions are actually these cosines that can go either as KCT minus Z or KCT plus Z. And we left it there. So we didn't really explore what that means, but I said, well, these are electromagnetic waves. So a note on those two forms that I derived. So there are many ways in which to do this. There's the super general way that I do in the textbook. And I use the complex notation for solving the wave equation, and it's the most general version, which means you get the complete phase degree of freedom. So you can have anything between a cosine and a sine, and you'll end up with two waves that are traveling in a plus Z and a minus Z. But if that's a little annoying to you, that's okay. So the way I did it in class was I used the real solution, and I said, okay, there's a cosine and there's a sine, and I wrote that as complex exponents because it's easier to do, and you don't have to deal with the trig identities. But ultimately, you'll end up with something that travels one way or the other way. And I said, let's assume that those look like cosines, and that allows us to decouple them, and then we don't have to worry about phases anymore. We are restricting ourselves a little bit. Just be aware of that. So there could be cosines, there could be sines, but that's not necessarily going to change the physical character, because the difference between a cosine and a sine is just where do you start the clock, or where do you put the origin. And these are waves that are traveling through vast regions of space. So where we put the zero, usually not super important. So having said that, what are we going to do today? So we're going to analyze those waves, and we made several assumptions when we wrote down those simplified versions of Maxwell 2 and Maxwell 4. The first thing is that we said that the wave is only varying as a function of time and z. Furthermore, we said that the electric field points in the x direction and the magnetic field points in the y direction. Now, that's a very, very specific type of wave, and that's known as what we call a plane wave. And what do we mean by a plane wave? But what we mean by a plane wave is that we say that there's a direction of propagation which is along the z-axis, so either plus z or minus z, and the phase of that wave is a constant across a plane that is perpendicular to that z-axis. So there are large planes where the phase is constant, and and then on top of that, the electric field doesn't vary across those planes either. So they're called plane waves. Now, plane waves are obviously a huge simplification, but it's a very, very handy model to talk about, because if you zoom in, you have a laser beam and you zoom into it well enough, you can see that in small spots you could consider those plane waves, and they're therefore a very, very handy concept. So they're an idealization, and they're definitely in the realm of infinitely thin lines that stretch the entire length of the universe. So they're handy concepts to think about, to get familiar with the way that these things work. But always you should keep it in the back of your head that these are approximations to the way that waves look like. Now, finally, there are also, if you look at the wave equation, we only considered waves that travel. But if you check the opposite sign of the solution set, you actually get evanescent wave. And for instance, evanescent waves are the things that take the quantum mechanical wave function and give you electron tunneling, which is something that I use in my work a lot. So this wave equation doesn't just show up in electricity and magnetism. It shows up in all sorts of different fields, and it's important to realize that sometimes it looks like a sine wave or cosine, and sometimes it looks like an exponential, and it all depends on the solution that you're looking for to determine, am I looking for something that's traveling, or am I looking for something that is exponentially decaying? And that's all given by the physical circumstances. So, final point: separation of variables. I hope that you've seen it before. You should have seen separation of variables in Math 280. If you haven't seen it before in your differential equations course, it's a really, really powerful technique. And once you've seen it once, you've done it a couple of times, it really is not a very complicated thing. But just be aware of that. You're limiting yourself. You're saying, I have this differential equation, second order with respect to z, so spatial second order, spatial derivative, and I have a second order with respect to t, second order derivative with respect to t. And I'm going to assume that my solution looks like a product of something that is exclusively a function of time, and then times a function that is exclusively a function of position, z. And that is, of course, limiting our solution set. So we're getting a solution, but we're not necessarily getting the only type of solution. So it's powerful, but just be very mindful of the fact that you might be throwing some stuff by the curb. Okay, so today we're going to look at the physical properties of those waves. and we'll look at the way that these waves carry energy, and then what their attributes are. Electromagnetic waves. All right. We, at the end of last class, had come up with an electromagnetic wave that looked something like this. And we said that there was only a z and a t component, and it was pointing in the x direction. It has some kind of a prefactor, and it was cosine, okay, ct minus z. And that was one solution. There was also a solution that was going in this direction. Plus c. And then the, and sometimes we'll have these, have different prefactors. And then there was a B field as well. So there was a B field that was, I do apologize, that was pointing in the y direction at some B component, 0, and let's call this minus cosine, okay, ct minus z, and then there's a plus y hat b0 plus cosine, okay, ct plus z. So these are related. You can tell this one is related to this one, and this one is related to this one. Now I want to just focus on one solution for now, because it's it becomes very, very messy quickly anyway, even if we don't try. Okay, so let's look at this one. So we have an electric field that's pointing in the x direction that is varying as a function of t and z. So the problem is that this is a thing that is a three-dimensional diagram, but on top of that, it varies not just as a function of z, but also as a function of t. So in addition, we have to draw the magnetic field. So we have 1, 2, 3, 4 dimensions that we need to take into account. And obviously that we cannot do in paper, so we would have to use some kind of a movie. So we'll have to do we'll have to take snapshots, either as a function of z, so let's say set z equal to 0 or set t is equal to 0, and then plot what these things look like as a function of spatial dimensions, right? So we have 4 coordinates that we should track, or 4 axes that we need to draw. And because we can't do that on a 2-dimensional piece of paper, we can only draw perspective drawings, certainly not anything more sophisticated than that. So we have to do slices. So let's first take the case where t is equal to 0. So we have the x-axis, the y-axis, and the z-axis. So let's call this z, and let's call this x, and let's call this y. So we have a cosine for the electric field that is going from here, through here, through here, back here again, something like this. So it goes like this. It's a cosine. Etc. So there's a electric field here, and that is that number E0, and that's our green solution. And now we have our the red component, that's our B field, and that goes from in the y-axis somewhere here, goes through the same point because it's the same cosine, but then instead it goes, hang on a second, goes through here. So it goes like this. It's a little hard to draw, but it's in the y-axis. So this is our B naught. And that's our B naught minus, if you will. So minus for the fact that it's a it's the term that has a minus here in the argument. All right. So let's look at what this thing is doing. Well, we have the phase here. This is where the phase is pi over 2. Okay, what do we mean by a phase? Well, the phase is whatever it is that we're taking the cosine of. So let's draw that. So we're going to call that the phase. So we're going to call that the phase, and it's a function of z and t. And this is the phase for the minus sign, right? So that's the phase for the minus sign. Right. So this is where it's pi over 2. This is where it's 3 over 2. And this is where it's 2 pi. All right. So the wave looks just like that, and our equation looks a little different when we have, for instance, a time a little bit later. So t is equal to 0. That's this one. So let's call delta t. So delta t a little later, it's going to look like this. So this point has moved to the side. So that's gone here. That's gone here. It's gone here. It's gone here. So this one now looks like this. So you see it has shifted in that direction. And the same thing with the red one. So the red one will have shifted to here, here. So it goes like this. I think you kind of see this coming. What's happening? Okay. It went a little too far. All right. So this has shifted in this direction as well. So something's obviously happening where we have this is that t is, let's call it delta t. So let's look at what's happening in that case. So we have a we have that phase that's a function of z and t, and for instance we can track the point where for instance this point starts here. That's where the phase is 0. So that point is where the phase at t is equal to 0, z, t is equal to 0. But then that's at t is equal to 0, so that's 0. And then we have the point has moved over here. It's still the point with the same phase because that's the thing that's moved over here. So that crest has now moved here. So now the phase is at some new coordinate z prime at some delta t, which is now equal to 0. So this is an implicit equation, and we can write this explicitly. So we have our phi at z. So this starts at the origin, so we start there. And instead of z prime, we do a delta z to get a delta z and a delta t. So we first have phi 0, 0 is equals to 0, means that k, c, t minus z is equal to 0. So that's what the phase is, because that's that blue function over there. And now the same phase, but now has moved over in both time and phase is still 0. So now we have a K, C. Now this point, so this is at 0 and this is at 0, so that's satisfied. This point has now moved to a C, delta Z is equal to 0. And now we can ask ourselves, what is delta Z over delta T? Well, we can factor out our K because our K is not 0, and we'll get delta Z over delta T is equal to C. And delta Z is in meters and delta T is in seconds. So this is the speed. So this is the, actually I should highlight that. All right, this is the speed. And since we're tracking the phase, this is known as the phase velocity. There's also an amplitude velocity. I don't want to get into the weeds here. And then this is actually 1/√, epsilon naught, mu naught. Now here's the big surprise. If you calculate that, C is 1/, epsilon naught, mu naught. That's 1/√885, 10 to the minus 12 times 4 pi 10 to the minus 7. You plug that into your calculator, you get 3 times 10 to the minus 8. That is the speed of light. And that's a big deal. So we started out with a very straightforward evaluation of what happens with two time varying electric fields and magnetic fields. And when we let them talk to one another, how do they talk to one another? And we're finding that these parameters that we have defined before, that epsilon naught and mu naught, when you put them together like this, out comes the speed of light. So the speed of electromagnetic waves is the speed of light. Now, later we will do stuff in media, and specifically dielectric media like glasses, and then we'll set that epsilon naught to something a little bit higher, so the speed's going to change a little bit. So this is the speed, as we call, as we say, the speed in vacuum. Let's talk about the sign of the phase. So we were tracking this particular solution, the one where we were tracking this part where the phase was given by this blue expression. And then we tracked how that was moving from here to there. And then we saw that the that part of the phase where we were getting an antinode here was moving to the right, even though there was a minus sign here. Well, of course, mathematically, it's easy to see that there's a minus sign here means a positive speed, because this still needs to be 0. So in other words, if this is positive and that is positive, that's the only way that it can be 0. So, or put it in another way, any kind of phase that you want to track as a function of time, when the time goes up, the position needs to go up in a commensurate manner given by C times delta T in order to make sure that we're still talking about the same phase. In other words, the fact that there's a minus sign here means that it's moving in the plus direction. So this is where sometimes a lot of confusions happen, and unfortunately it's not helped by the fact that sometimes I mix up my references too. So let's clean this up a little bit. So let's call this, even though there's a minus sign here, let's call that the solution for the one that's moving in the plus direction. So we're going to call this the plus direction. We're going to call this the minus direction, this the plus direction, and that's the minus direction. And now the same thing happens when we're looking at a solution where where we're tracking a phase, but now we're using this thing with a plus sign. That means that if time goes up, if we want to keep the phase constant, then time goes up, then z must be going down. So now we're talking about a solution for the wave that's moving in this direction. So that's the issue of the sign of that phase. Okay, so next thing we want to look at is the actual wavelength. So the wavelength is always defined as, you know, this part where the phase wraps by 2 pi. So it will be the distance between these two. Or, put it another way, the phase from here to there amounts to 2 pi. So 2 pi equals k ct minus z. And we're doing this for one particular time, so we can pick t is equal to 0 if you want, just to see what happens with z. So then we have 2 pi is minus kz, and then that's the definition for the wavelength. So that is what we call z is lambda, and that means that that is 2 pi over k, and I'm throwing away the minus sign because we can, and k is 2 pi over lambda. So that's the wavelength. So that's the wavelength. And k is the wave number. They are each other's inverse with a 2 pi. Okay, so that's the periodicity of the wave in space. You know, wavelength and wave number. Now let's talk about the periodicity as a function of time. So now imagine that you place a screen here, or you know, somebody's just paying attention to what's happening, and it's looking at the wave that is moving in this direction. So in that case, we want to know what's happening when we pick a position z, and we want to see what's happening with the E field or the B field. So pick, for instance, pick z is 0. What is the behavior versus time? And then what is frequency, and what is angular frequency? And I'm going to pause this for a second, so I want you to just look at it yourself. And then when you're ready, this is where I would usually use Nearpod, but because we're doing this asynchronously today, when you're ready, just do it again. All right, so now we're on the other side of the other pause button press. So we're picking z is equal to 0, so the electric field for the wave that is traveling in the positive direction. And now I'm seeing, by the way, that I messed up on my signs here as well. I told you the pluses and the minuses are confusing. So we're looking at this one. So at z is equal to 0 as a function of time, it is it's a vector, it's x hat e, some 0 plus, and then it's cosine. And where are we? Z is equal to 0. Okay, so we have kct. kct. All right. Now, what does that mean? Well, this looks just like your regular definition for something that is periodic as a function of time. That is, for instance, so same prefactor, 0 plus cosine, and it's either omega t or 2 pi f t. Okay, so therefore, Kc is omega. Kc is omega. And there you go. So Kc is omega is 2 pi f. And that's the frequency. So the putting everything together, we have Kc is omega. So we also have K is 2 pi over lambda. That's the wave number. Or lambda is 2 pi over K. That's the wavelength. And finally, we can combine this with this, and we'll get the usual relation. You'll get K times C is equal to 2 times pi times F. So K, which is 2 pi over lambda. So 2 pi C over lambda is 2 pi F. So that means 2 pi C over lambda is 2 pi F. In other words, C is lambda F. And this should be a well-known relation. This is from any kind of wave-like phenomenon, something that varies as a function of frequency, like this. It's got this wavelength, it's going to give you this speed. So these are your central relations for electromagnetic waves in particular. Now let's talk about the relation between these prefactors for B and for E, because I was saying that the solution for the B field is coming from the wave equation for B, and the solution for the E field is coming from the wave equation for E, and they're not independent. So once we have the E field, what is the related B field? Well, we can find that from these two relations that we had used to connect our two solutions for Maxwell 2 and Maxwell 4. For instance, the first one, and it's the easiest one, that said that D relation between E and B naught. Okay, so dE dZ equals minus dB dt. So we derived that from our Maxwell 2. So this was from Maxwell 2. You can revisit your notes if you want. All right, so if dE dZ is equal to minus dB dt, what does that look like? Well, this is d dZ of E, which itself is, let's call it, this is about not the vector property, but the amplitude. So there's an E naught, and we're dropping the plus. We have a cosine K C T minus Z equals minus ddt of B, which is B naught, and then that's a cosine K CT minus Z. Yep, that's 3 parentheses. Okay, so when I take derivative with respect to Z, we'll get an E naught. The cosine is going to become a sine with a minus. And then because we are taking the derivative with respect to Z, we also have to factor the chain rule. And that means that we pick up a minus from here and a k. So that becomes plus E naught k sine, and then whatever the argument was, so that cosine stays the same. All right. And now here, we're taking, again, our derivative of t. Now we have a b naught, and we're taking derivative with respect to t, which means we pick up the c and the k through the chain rule. The cosine becomes a sine with a minus, but we already had a minus, so that becomes plus. So that's k ct minus z. Okay, so fortunately, you see this is sine kct, that's sine kct, so that's good. So that shows that there's nothing funny going on. There's nothing time dependent about this relation. And we find that E naught, let's write that here. E naught is C times B naught. So for a given electromagnetic wave, the magnetic field component times the speed of light, that's a massive number. So that is 3, 10 to the 8, gives you the electric field. So usually the magnetic field component is much, much smaller than the electric field component for an electromagnetic wave. Now, that is the case in SI unit, which is the SI units are the types of units that we're using. And in that case, that's the case. There are different units. There is, for instance, the so-called Gaussian unit system, which we don't do now, but I'm planning to use them when I'm teaching graduate E&M next semester. And in that system, the E naught and the B naught are of the same magnitude. So that means that you're using a different unit for B, such that the C disappears here, and it makes life a lot easier. Okay, so that's the relation between E naught and B naught. Let's talk about energy density. So remember that we had the energy density in a capacitor was some kind of a U, and it's a lowercase u, and it's sub E, and it was 1/2 epsilon naught E squared. And remember that by energy density, we mean, because we use lowercase, that is joules per cubic meter. So that's the energy density stored in the electric field of a capacitor. And for in an inductor, this is one of the homework problems, equals, U sub B, it's B squared over 2 U naught. All right. Now, if we expand this concept that the energy density, if we express it as stuff that's carried by a B field or an E field in the space between conductors, or the space enclosed in an inductor, then we can say that the total energy density in an electromagnetic wave, is U E plus U B equals, there we go, epsilon naught E squared plus B squared over 2 U naught. But we know that our E naught is C times B naught. So we can we can change this. We can either write this completely in terms of B, or we can write it in terms of E. So it's 1/2 epsilon naught E squared plus C squared B squared over 2 U naught. Oops. I went the wrong way. E squared. See, check, double check. Yep. Okay. So that's the energy density. And now we can factor out our 1/2 E squared. Okay, that is epsilon naught plus 1/mu naught C squared. And that is 1/2 E, oops, epsilon naught E times 1 plus 1/mu naught epsilon naught C squared. And this was 1, because we had defined C squared as being 1/mu naught epsilon naught. So this is 2. So the average energy is 1/2, 2 epsilon naught E. And this is not supposed to be mu. Okay. Or expressed in terms of B. So we'll change our E into a B. So we'll have U equals 1/2 epsilon naught C squared B squared plus B squared over 2 mu naught. And now we'll factor out the B squared and a half. And we'll pull out the mu naught as well. So then we get here epsilon naught mu naught C squared plus 1. And this, because this is 1 again, is therefore 2. So the energy B squared over mu naught. Now, this looks like just kind of a funny exercise, but I want you to look at this very carefully. So the magnetic field energy density is B squared over 2 mu naught. And the total energy density is this, 2 times as big. The electric energy density is 1/2 epsilon naught E squared, and the total is 1/2 epsilon naught, is 2 times bigger. Epsilon naught times E, I forgot my squared. Hang on a second, that is sloppy. There we go. E squared. So this is important. It means that the energy density that's carried by the electric field component is equal to the energy density carried in the magnetic field component. And that is counterintuitive, right? Because I said here that the magnetic field is much, much smaller than the electric field. And that is because this is about weird units, right? This is about what do we choose for the units of Tesla, and what is the unit that we use for newtons per coulombs or volts per meter. But now, when we're talking about energy density, we're treating the electric field and the magnetic field on equal terms. We're saying we're going to convert them both into how many joules does that translate to. And it turns out that if you do that, you can see that they are playing exactly the same role. And it makes a lot of sense because you have a lot of energy in the electric field component, and that energy sloshes around between the electric field and then into the magnetic field. And then that energy that's in the magnetic field sloshes back to the electric field. And because it's sloshing back and forth, makes a lot of sense that they are the same. So U, E is equal to UB. And that is because now we're treating the fields on equal footing. Finally, let's talk about what happens when that energy flows. So let's say we have the energy flowing in that wave. So we have some kind of a wave, it's traveling in this direction. You know, there's a sine wave and there's a sine wave, E field and V field. And now we take a volume here, and the total energy that's in this volume, is U, little u times V, where V is the volume. Okay, and let's call this thing length L, and let's give this thing surface area A. Then the total energy here is, let me go back to this. So it's little u times A times L. Okay. Now, all this energy is being carried by the wave. It's being carried from here to there. So if we put an imaginary surface here, and we ask ourselves how much energy flows through that imaginary surface, flows through this imaginary surface. And then we have to ask ourselves, well, how long are we counting? Well, let's say that this size is given by some C times delta T. So we start a stopwatch. We say, okay, now tell me how much we got. Then we get the total energy is going to be U times C times A times delta T. All right, so that's the total energy. And now we're using a surface, and we usually like to normalize things. So let's say, okay, how much energy flows through this surface per square meter? Because if we make this thing bigger, so make the surface bigger, we also get more energy. So it makes sense to divide out that thing. So then we're talking about the energy that flows through it. So that's delta U. So that would be delta U over delta T. And then we divide it also by the surface area. And then we get U times C. Now, U times C actually has symbol S, and it's called the pointing vector. And it's got units because it's energy per unit area. So the units of S are joules per square meter. And now, because the energy is carried by both the electric field and the magnetic field, we can split that up in two parts, and we can say, well, it's carried by both, so we need to use both the electric field and a magnetic field component. So in that case, we're going to say that the energy, if we use this previous expression that we had for U, so let's say U was this one, right? There you go. But now we're going to use both the E and the B component. We're going to call this E times B. Or generalized, it's, oops, 1 over mu naught, E crossed with B. And now we're talking about a vector. So we generalize this. So this thing, ladies and gentlemen, is the pointing vector. So we take the E field, we take the B field, we cross them, cross product, right-hand rule, gives us the pointing vector. It tells us how the energy is flowing. Now, this thing is carrying not just energy, but it is also carrying momentum. So a dimensional analysis is the easiest way to see this. So if you have some kind of a wave that's carrying this kind of energy in a direction that is given by the cross product of E and B, then this pointing vector tells you how much energy per unit area you've got. Then the power delivered to a surface, power delivered to its surface is that same thing that we had before. So that's the pointing vector times A. But that is actually power, right? So it's joules per second. But joules is force times distance. So that's F times delta L over delta T. And that distance and that time interval is the speed of light. So that's F times C. So if that's the power, that's the force, then the force per unit area is F over A. It's that force over A. So it is S, the pointing vector, divided by C. And force per unit area actually has a name, and that's called pressure, right? Because this is in newtons over meter squared, and that's the unit of pressure. So this is pressure. Okay, so this concept is known as radiation pressure. So and it's P and it's S over C, and it depends a little bit on whether the energy is being absorbed or whether it's being reflected. There could be factors of 2 here, but for now that's really not important. So the radiation pressure, what is the radiation pressure? Well, it is exactly what you think it is. So if you are standing here on the surface of Earth and you're facing the sun, there is electromagnetic radiation that's coming from you, and it is hitting the whatever faces part of your body that is facing the sun. And the sun carries a lot of energy. You can feel because that part of the body gets hot. But also because it's dumping all that energy only on one side of your body, not only does your body become hot, you're also being pushed away a little bit. Now, on Earth, that is a tiny effect. So, for instance, in a it's only 6 micropascal. So on Earth, it is 6 micropascal, which is really kind of tiny, right? So atmospheric pressure is 10 to the 5. So 1 atmosphere is 10 to the 5 Pascal. So this is really tiny. It's a 10 or 11, depending on how you want to look at 6, 10 or 11 orders of magnitude. So it's tiny. But on Mercury, it is much closer to the sun. It is about 10 times bigger. But this has a real application in solar cells. So solar cells. What is a solar cell? Well, imagine that you're in space, right? So you have the sun, and you're in the sun here. And now, let's say you want to go from Earth. So this is Earth to Mars. Oh, Mars is the red planet. Here we go. Mars. Now, what you can do is you can launch a spacecraft that has basically a really big surface area A. And this thing, if you point it right, is going to feel a pressure due to the fact that there's solar radiation falling on this thing, which means that it's going to feel a force in this direction. And therefore, it's going to move from here to there. So if you time it right, you could go without using any fuel other than the fact that the sun is burning whatever hydrogen inside. But it doesn't, you don't need to launch any rocket fuel, and this thing will basically go from here to there because you're not using any energy. This thing can be light, and it could be, a sail that you deploy, right? So you launch a rocket, it expands, and it becomes bigger and bigger and bigger. And then if you time it right, you can basically hitch a ride from here to there. Now, obviously, that's not going to be very fast, 6 micropascal, but it's a little bit like free shipping with the postal service. The fact that it's free usually means it doesn't go very fast, but hey, it's free. So there you go. So ladies and gentlemen, that's electromagnetic waves. So next thing we will do is we will take a step back from the full electromagnetic wave description, and we'll try to simplify our way of talking about electromagnetic waves a little bit. Makes life a lot easier in the same way that we can have a very domain-specific way of talking about electricity and magnetism in the context of circuits, where we have just a handful of equations. There's no more or hardly any differential equations that we'll need in order to describe circuits once you get your language right. Thank you very much.